Let's start lecture 8 under the lecture series cathodic protection methods, and today's topic will be the continuation of what we discussed in the last lecture, that is guidelines for better design. The course is and this better design towards having a better protection from corrosion. Now, two things we talked about. One is tank design, and second is joining methodology. We said that welding is better, over rivet. So let's list down other guidelines. Easy replacement. If any component in a system is undergoing higher corrosion than the other components, it's better to replace, it's better to have some sort of arrangement so that that component which is undergoing heavy corrosion be replaced quickly as well as without disturbing the other components, like pumping system, where pumps are actually going through severe corrosion. In case of pump, one of the major corrosion processes that is basically cavitation. So we should replace pump quickly without disturbing the pipeline arrangements. So like one example is pump replacement without disturbing the piping system. Similarly, if we see that there would be a possibility that bolts are actually going through a lot of corrosion process, that means the fasteners, so we must replace those fasteners quickly, okay, because those are the small components, it's very easy to replace. Then we have avoidance of stresses. Mechanical, thermal, fabrication related stresses. So coming to this residual stress part, one classic example is related to knife line attack in stabilized stainless steel. See, if we take, this is knife line attack in so now this particular aspect has been already discussed in our previous lectures, but still in short we can discuss this. See, if we have a tank made of this stabilized stainless steel where we have titanium or niobium, which are greater carbide formers because they have higher affinity towards carbon rather chromium. So they will form carbide, taking carbon from the solution, and chromium will be left out because there will be no carbon to form while it is cooled slowly around the temperature of 450 to 650 degrees Celsius. So that is called stabilized stainless steel. Now, sensitization of stabilized stainless steel can also happen due to fabrication method, poor fabrication. What happens if we weld? Let's say this part is weld, this segment is weld. After welding, this is the welding part. So after welding, if it is a thin sheet material, so then one has to go for a little bit of, if one goes for stress relieving operation, so after welding, stress relief operation. And if that operation happens around 450 to 650 degrees Celsius, then again what happens after welding around this zone, narrow zone actually, because we do arc welding, not gas welding. Gas welding is not preferred welding method for stainless steel. See, if we do arc welding, temperature goes beyond 1600 degrees Celsius. So everything melts, and while everything melts, this titanium carbide or niobium carbide, those are formed during formation of stabilized stainless steel plate, those will also melt. So that means again carbon will go back to the solution. So when carbon goes back to solution, and since this is a thin plate, a thin sheet, so the cooling rate would be very fast. So now all the carbon as well as those elements in those narrow zone, this narrow zone will go to solution. So now titanium, niobium, carbon, chromium, everything is in solution, and of course there will be thermal stress because of the thin sheet welding. Now if you stress relief at that temperature, since carbon is already there in the solution, so a lot of carbon is available for the formation of chromium carbide, and this temperature zone, the carbide formation for titanium and niobium, those are not that faster. Okay, the kinetics are hindered, though they have higher affinity, but kinetics are hindered. So then the chromium carbide can form again, and of course the chromium carbide, when it forms, this is the grain boundary, they will again form along the grain boundary. Those chromium carbide will form, and if chromium carbide forms, that means the stabilization effect is gone. And once chromium carbide forms, definitely there would be a narrow zone of depleted chromium, and again that narrow zone will be susceptible to intergranular attack. So then again intergranular attack would form, and then there could be a possibility of a sharp crack near that particular weld zone. That sharp crack would happen, and that sharp crack is nothing but the knife line attack. We call it knife line attack. So the way to resolve this part is, one way is we take it to around close to 1100 or 1200 degrees Celsius. So then what happens? We, by heating quickly between this temperature zone, so that titanium niobium carbide will again form, because at a higher temperature beyond around 1100 degrees Celsius, around 1050 degrees Celsius, chromium, titanium nitride, titanium carbide and niobium carbide will form, and they will again avoid chromium carbide to form whenever that particular material is slowly cooled after heating there, of course. So if you heat there, so that your stress is relieved, and when you cool slowly, no stress is generated again, fine. But already you have removed all those carbon from the solution by forming titanium carbide and niobium carbide. So that's the procedure one should follow, and once you follow that, then definitely chromium carbide is not forming at all, because the chromium is not finding any carbon to form. So that knife line attack can be resolved, right? So similarly, mechanical stresses can also be possible, like when you deform some places, accidentally some place is having extra load or extra stress, that particular segment can get deformed, and immediately you can have a higher activity from that zone, and that zone can actually go under SCC or stress corrosion cracking. Fine. So, this is the avoidance. It is better to avoid mechanical, thermal or fabrication stresses. At the same time, we should be careful for further processing to remove those stresses, like what we have seen in case of knife line attack in stabilized stainless steel. Now, fifth point, avoid electrical connection between dissimilar metal. Now, we have been telling this, we will show some examples, and more examples will come in subsequent lectures. So, it means that if we, let us give an example like copper and iron. So, the copper in NaCl or seawater, copper sits much higher in the galvanic series compared to iron. So, copper would act as a noble component and iron will act as an active component. So, the cathodic reaction here, it will be oxygen reduction, O2 plus 2H2O, because it is a neutral solution. This reaction would happen. This is a strong oxidation reduction process, and oxygen is a basically strong oxidant. Now, the requirement of electron will be coming from iron dissolution. So, this iron will dissolve. Now, if we connect them, this problem would happen, because there will be easy passage of electron and the current will, this is where the current will flow and iron will dissolve and copper will be protected, because copper will be cathode. This is cathode. We know that the metals and alloys which are sitting higher up in the galvanic series in that particular solution would always act as cathode, and this will be anode, the materials which are sitting below. So, we should avoid this dissimilar metal connections. So, that means we should make components from the same metals or alloys, but practically this is impossible. Okay. So, we have to make sure that those connection, even if there is connection, there should be a proper insulation, and that connection, it should not be electrical connection, rather those two components sitting wide apart in the galvanic series are separated within insulating material. Now, this is one part, and the second part is, even if we have to use materials which are different in terms of their electrochemical behavior, then we should choose materials which are closely sitting in the galvanic series. So, the galvanic effect will be low. That means, and third part is, even if we have, let us say, connection between two alloys which are sitting little wide apart in the galvanic series, we must make sure that the area of the cathodic component should be less. Okay. And at times we have to also coat that cathodic area, even we can leave the anodic area exposed. That is also better. Okay. So, couple of things we have to make sure while having this, because whenever we have a connection between dissimilar metals, the metal which is active would dissolve quickly. So, couple of things we have to make sure. One is, choose same alloys or metals for fabrication, for making any component. And practically this is impossible in most of the cases, practical impossibility. we can write in most of the cases we have to have dissimilar metals. Now, if that is the situation, then we should choose or select closely spaced in galvanic series. So, what it will do? The effect of galvanic attack of active component will be very less. Okay. So, that would be possible, fine. Now, the third guidelines could be, if we have widely spaced metals and alloys components, then insulating components, of course metals and alloys, widely spaced in galvanic series. Okay. So, that way we do not have electrical contact and we can avoid this, we can avoid galvanic corrosion. And another important part, which is basically coat cathodic part, okay, or area of cathode should be less than anodic area. Okay. So, these four things are to be taken care of. Now, are to be considered while designing machine components or equipments or practical applications, wherever such situation is arising that electrical connection is essential between dissimilar metals. So, we have to have those issues, those design factors are to be considered. Now, on everything we will show some examples later on, because this particular aspect is very common and we have to have a greater discussion on this. At least one example we can show, that the last part what we talked about, the last part, if we see, if we consider welding, let us say we are doing welding, two parts are welded. So, this is the weld part. Okay. So, when we do welding, we can make it cathode. Cathodic material can be used as a welding material and this can be anode. Better is using the same material for welding, but if it is not possible, then we have to use weld material which should be cathodic to the welded parts. Why it is to be cathodic? Now, what happens? There are two situations, let us consider. One is, let us say this is one where this part is anode and here this part is cathode and this is then cathode. So, in this case anodic area is very large, much greater than cathodic area. because the weld material is cathodic to anode parts which are to be welded, and it is a small zone where weld material is used. So, the galvanic effect would be very low in this particular situation. The anode definitely would have corrosion. So, around that particular portion, the close to that zone, there would be possibility of galvanic effect, galvanic corrosion of that anode, but that influence will be much less. And in order to understand that, please go back to the previous lectures, on those previous lecture series, please go back there. But in this case, cathodic area is much larger than the anodic area, because there is a small portion where anodic weld material is kept. Okay. So, then the dissolution of this anode would be much higher. And if this is the case 1 and this is case 2, so case 2 would be much higher than the dissolution in case 1. Dissolution of anode would be much higher than the in the case 2 rather than the case 1, because case 1 we are having favorable area ratio for better corrosion protection. Okay. We will have lot more discussion, lot more pictures over this on this particular topic, we will discuss later. The 6th point is to avoid sharp bends in a piping system. Now, this actually, if there is a sharp bend, then there is a problem of erosion corrosion, and this erosion corrosion is related to impingement plus stress plus wear plus corrosion. All those 4 factors can be there. If we have a kind of a smooth bend without sharp bend, actually erosion corrosion can be avoided to a great extent. Let us see some examples. Now, if you see a pipe system, let us say I take this pipe system, let us say if the system is like this, then water flow is coming like this and water flow is going like this. So, water is hitting in this zone. So, this zone is susceptible for extra bit of erosion corrosion. So, the best way is to handle this, you can have a smooth bend, rather instead of this you can have this. Okay. So, then that impingement factor can be avoided. Okay. So, this green color part is the modified design. In fact, in a pipeline system, always you have to have one angle there fitted, with that angle is actually having a bend. Now, this is one instance. The other instance is, if you have a piping system, if it is a smooth one, let us say this is the bend and fluid is passing through, let us say aqueous medium along with let us say even if it is emulsion, it is going like this. But if it is a smooth wall, inner wall of the pipe, then the flow would be linear and then there will not be much of issues. But if there is a situation like this, if the inner wall has uneven portion like this or like this. Okay. So, then there will be an issue. Issue is there will be a lot of turbulence. So, the turbulence pattern could be like this. So, the fluid is flowing and then there will be a whirl, and this particular portion will have erosion corrosion. And similarly here, fluid flow is like this. Fluid flow can have a whirling action here. So, again this particular part will be subjected to erosion corrosion. So, this is another instance. Instead of here, it is not about sharp bends, rather having protrusion or dent. Protrusion or dent. So, this is the dent and this is protrusion. Okay. So, that is also not good from the point of erosion corrosion. It actually hinders the flow pattern of the liquid. Now, there could be a situation like using deflector so that it can avoid the impingement on the tube wall. So, that deflector is a separate part which is added to the tube. So, now if the design is like this, if the design is like this, water is coming like this. So, it can again hitting here before it goes like this. So, this part again erosion corrosion point. Fine. So, now again that can have a modification. The modification could be it can have a modification like this. Fluid is coming like this and then going like this. So, the fluid action can go towards this, and here I can put a deflector. So, this is my pipe wall and this is my deflector, and deflector is little harder so that it can resist or withstand the impinging effect. So, now we have to have smooth bend or a kind of radius there in the bend, no sharp bend, no protrusion, no dent, as well as provision of having deflector or buffle plate. So, deflector or buffle plate. So, that can avoid erosion corrosion. Right? So, first thing is avoid sharp bend, and the second part is in case there is a possibility of erosion corrosion. So, there we can use deflector or buffle plate to take care of that particular wear action. Now, another design aspect could be if we consider a pipeline like this. Okay. There could be a possibility of this bent portion, we can have a separate material. Okay. This bent portion, we can have a separate material which can be a little harder material than the pipeline system. And also instead of making it sharp, so one design could have been like this. Okay. So, this is not a good design, this is not a good design. So, rather we put a bent portion there, so that water hitting on the corner portion is less. Okay, so the water flow would be controlled, and then it will not have much of impinging effect on the opposite wall. Now, the seventh point, okay, fine. So, let us continue this discussion. There could be possibility that a pipeline system, let us say this is my pipeline system, instead of this inner wall of the pipeline system is also critical. Let us say instead of having a smooth line, if there is a dent, let us say there could be a possibility of dent. Okay. So, instead of that, the pipeline design could be like this, or there could be possibility of little hump. So, now this particular position as well as this particular position, there could be possibility of lot of turbulence. Okay. So, now this turbulence can also have erosion effect. Okay. So, we have to avoid this kind of hump or dent. The inner pipe surface should be as smooth as possible, then we can avoid turbulence. So, this turbulence avoidance can also be possible if we have a smoother inner pipeline surface. So, we have few more guidelines. So, we will talk about those guidelines in our next lecture. So, till then, thank you.